this was our story from yesterday. The inverse function theorem, the derivative of f inverse is equal to the reciprocal of f prime, evaluated at f inverse of x. And I want to do the following things. I want to prove this again. I want to have a clear picture of what's going on so that this will make sense to everybody. And then I'd like to extend to consider what this looks like when we use Leibniz notation on it. What does the derivative of our inverse look like when we are using Leibniz notation? Okay? So, the proof of this is delightfully simple. We begin with the fact that f of f inverse of x cancels to give me x back, because that's what inverse do. That is what it means to be an inverse. So an inverse function is a reverse lookup. Take an x value, find where it came from, and then apply f to it, sends it right back to its x. So our big picture here is that I have a point x like so, and well, actually my point x would be over here in my domain like this, and so we would have f inverse of x would take us to some point y here, like that, and then f of y would take us back to that point x. So that's the picture, the set picture. So this is what it means to be an inverse. If I now simply differentiate with respect to x on both sides, then on the right-hand side, of course, I get 1. On the left-hand side, I have chain rule. Outside, inside. The outside function is f, and so the derivative of the outside is f prime of f inverse, times the derivative of the inside, which is f inverse prime. And now it's a simple matter of solving by dividing. F inverse prime of x is equal to 1 over f prime of f inverse of x. Now, here's the picture that goes along with it. Suppose I have some function f, and I'll make my f look like this. First of all, is this function a one-to-one function? Yes, it passes the horizontal line test, and therefore it is one-to-one, and therefore it has an inverse. And I can generate the graph of that inverse by reflecting over the line y equals x, so that the graph of my inverse is going to end up looking something like this. Okay. Now let me pick a point, a comma b. So b is equal to f of a. And therefore a is equal to f inverse of b. When I pick this point a comma b, then over on the graph of the inverse, I have a matching point b comma a, like that. Okay? And if I now draw myself lines tangent to f at a, then the slope of this line is f prime of a, and the slope of the tangent line at the matching point is f inverse prime of b. Okay? Now, here's the only point that I want to make. If I draw for myself a rise and a run, and I label this guy dy, and I label this guy dx, and when I come over to here, because my x's and y's are reversed, this length right here will be the length dy, and that height right there will be the height dx. So that the slope of this line is equal to dx over dy, which is the reciprocal of dy dx. And that that is what the inverse function theorem is saying. That dx dy, the slope of the inverse, is the reciprocal of the slope of f, but evaluated at the matching point. Does that picture make sense? Yes, sir. You know it for life. Mm-hmm.
Lower function is f of x.
The lower function to be f, and this would be f in the inverse.
And then
Let's give it a different label. Maybe this can be g, and that can be g inverse. Okay.
then it'll be g of inverse of g of x, or the graph is derivative of y over 3.
Yeah, the point is that the slopes here will be reciprocals of each other. And it doesn't matter what you label as y and what you label as x. Yeah.
So you don't have to put negative sign.
There is no, that's a good question. We don't want to confuse it with something else. What kinds of lines have negative reciprocal slopes? Perpendicular lines have negative reciprocal slopes. This is not related to that. Yeah, good question. Now it occurs to me, I didn't put this in our plan, but I wanted to take a look at any homework questions you had. Did you guys all find the answers to them last night when I posted them? Did you find the answers? Okay, let me show you on Edmodo. Here we go. Right here. Answers to inverse function theorem exercises. Okay. And also, while we're here, yes, your quiz is tomorrow. Okay. Okay, so just very quickly then. For the first one, your inverses should be these three.
Yep.
For number 2, well, let me go to here so we can have room. In number 2, we have this function, g of x equals 3x squared for x's greater than or equal to 0. And I ask you to find the inverse here. So if I set here, now I have a choice. Either x can be equal to root y over 3, or x can be equal to negative root y over 3. We call this a branch choice. And we make the branch choice based upon the domain. Notice that my x's have to be non-negative. So that means I'm going to choose the positive root. And that gives me f inverse of y. If I want now to evaluate f inverse of x, I substitute x. And get f inverse of x equals root x over 3. And in this problem, I asked you to compute the derivative of the inverse in 2 different ways. First of all, because I have the formula, I can simply take the derivative using derivative rules. I observe that we have outside, inside. Outside is square root, inside is x over 3. And the derivative of the outside is therefore 1 over 2 root x over 3. And the derivative of the inside is 1/3. And so I get this, or something algebraically equivalent to that. This could also be simplified to 1 over 2 root 3x if you wanted to. So that was simply finding g prime of x, g inverse prime of x, because I know the formula for g inverse, and then you can differentiate it like any other. Or I could appeal to the inverse function theorem and say that g inverse prime is 1 over g prime, evaluated at g inverse of x. And Clara, now we're clear that this does not refer to multiplication at all, right? So I need to know what g prime is. Going back to g, here's g of x right here, I can compute that g prime of x is equal to 6 times x. And therefore g prime of g inverse is going to be 6 times g inverse. But what is g inverse? It is root x over root 3. And we get the exact same result we got. So there was a two-step process using the inverse function theorem. First, I needed to find what g prime was, and then I needed to evaluate that at g inverse. Good? If f of 1 is 3 and f inverse of 1 is negative 2, what is f inverse prime of 3? We can immediately write f inverse prime of 3 using the inverse function theorem as 1 over f prime of f inverse of 3. And now I need to go back to the information to find f inverse of 3. What I find is that f of 1 is 3, so that means that f inverse of 3 is 1. And I can now replace f inverse of 3 with 1 on the inside. And f prime of 1 is given to me as negative 2. And then finally, well, number 4 is exactly the same way. So I'll let you check your answers against the answers that I posted. With all of that in mind, let's see, where are we? What I'd like to do now is to extend our inverse function theorem to situations where we are given a relation between x and y, but not an actual function. So let's go back to that relation that we had for our quiz. X squared y plus y squared is equal to 2. And in the quiz, I asked you to find dy dx. But now I want to ask a different question. What is the derivative of the inverse of y? And the derivative of the inverse of y is going to be the derivative of the function that finds x given y, the reverse lookup. And we're going to write that very naturally as dx dy. Take a look at this and see why this is the derivative of the inverse. What does the inverse function do? Given a y, find x. So if my function is y of x, and its inverse is x of y. And the derivative of that inverse is going to be spelled dx dy. Just like the derivative of the function is spelled dy dx. Does everybody see that reciprocal relationship, which we are exchanging x's and y's? And the meaning of the inverse function theorem in light expectation of this is that dx dy is simply the reciprocal of dy dx. That's it. Oh, that makes a whole lot of sense, doesn't it? The derivative of the inverse, dx dy, is simply the reciprocal of dy dx. And that notation, even though this looks like a compound fraction, it's not really. What it really is the reciprocal of a rate of change.
we still found dy over dx over dy, like what we did before, and 1 over that.
Actually, we're going to make it even easier. We'll come back and compare it to our dy dx in just a minute, right? But to find dx dy here, I am going to find dx dy by differentiating both sides of my relation, look at that, with respect to y. And then I can get dx dy directly. On the left-hand side here, product rule again. So we're going to have first times the derivative of the second, plus the second times the derivative of the first. And then I need a little more room, plus dy of y squared. But now watch what happens. The derivative with respect to y of y is 1. But the derivative with respect to y of x squared is 2x times dx dy. See how convenient that is? Yes, sir.
Because dx over dy is
Yes, you could write that in x prime if you wanted to. Then the derivative with respect to y of y squared is simply 2y. Now, how do I find dx dy? I've got terms with dx dy and terms without, so I'm going to collect all the terms without on the right-hand side by subtracting. And dx dy is equal to negative x squared minus 2y over 2xy. See? Easy. But now, let's go back and compare it to our quiz. It's not the same. It is the reciprocal.
You put 1 over this.
Dy dx is the reciprocal of dx dy. And that's it. That's the inverse function here. Questions? Comments? Or jokes? You look like you have a question. Okay? Yes?
every time you go into the function and multiply one.
So, I'm not sure what you're asking. The reciprocal of a simply means 1 over a, or a to the minus 1 power. Okay? So reciprocal is just 1 divided by a.
And you want to get
What? Of x?
6. You want to get f prime reciprocal of f prime of x.
Then that would be 1 over f prime of x.
So if f prime x is equal to 3, then we always
Yes, sir. But I get the sense that's not your real question. Because so far we haven't done anything with inverses yet. So is this your question? Okay. Yeah. Notice that there's 2 things going on in the inverse function theorem as I write it. And the first thing that we have to be careful about is that this guy right here is not an exponent. In this expression right here, a to the minus 1 for the reciprocal, this is an exponent. It means a to the minus 1 power. This is not an exponent. It is unfortunate that it looks like an exponent, and it is a fault of mathematics that the symbol that is universally accepted looks like an exponent. It doesn't mean an exponent. It is not the case that f inverse of x is the reciprocal of f of x. Generally, in general, occasionally, rarely it is, but that's not typically the case. Okay. Is it ever the case? You know, I gotta think about this. Can I have a function whose inverse is in fact its reciprocal? Yeah, one. F inverse F. Actually, I think that's generally true. I don't think there is a function whose inverse is the reciprocal of that function. I have to think about that more carefully. But it is true that the derivative of the inverse is the reciprocal of the derivative of f, evaluated at the inverse. And that's our inverse function here. So notice the weird interconnection of these two ideas, reciprocals and inverses. Yes?
If the boy explain,
It is not.
but if then can use chain.
Oh, if it were, yes, you would use chain rule. And the way that you would write that, if you mean for this to be an exponent, you've got two options. If you want to say f of x to the minus 1 power, this is the cleanest way to say that, so that nobody is confused. But if you have to use a negative 1 as an exponent, then write it like that, so that nobody thinks that you're doing it in reverse. So this is equal to this, not equal to that. Good questions. Huh. So, take this word. So we would have to have x equals, we would have to have f of x is equal to 1 over x. Yeah, I don't think there is any such function. I think this is always true. And f inverse of x is never 1 over f of x. But that's a conjecture on my part. That I never proved for it yet.
Oh, lower x.
No, actually, if f of x equals 1 over x, then f inverse of x is equal to f of x, not 1 over f of x, because 1 over x is x. Yeah. Good. Any other questions? A way that can be proven. How about we use the inverse function there to prove it? I wonder if we could do that. If f, okay, I'm gonna turn off the recording of this one. We're just gonna do some exploration.